So my name is Andrew Farmer, and as Kathleen said, I'll be talking about some DSLs that we developed for interactive web services. This is work with my advisor, Andy Gill, who's sitting in the back. So, oops. Of course, I immediately slipped the wrong thing. So our motivation here is we want to create GUIs for these tools that we're developing to do interactive transformation of programs. Specifically, this is the Hermit project, which, if you guys are here on Thursday, Haskell Symposium, you'll hear about, so I won't talk too much more about that. But we want to develop GUIs for it, and we don't want to be stuck in that horrible place where you have to maintain dependencies on GUI libraries on multiple platforms and stuff. So what we want to do is we want to target web browsers, because we figure everybody has a web browser that works on the computer. And most web browsers support roughly the same capabilities, although they all support them in different ways. But thankfully, there's a bunch of people out there that spend a bunch of time developing JavaScript libraries that handle all this for us, like jQuery. So we want to use that capability, but we don't want to have to write a significant portion of our code in JavaScript libraries. Partially because if you've ever developed a web application, you end up with some of your application logic on the server and some on the client, and you have this delicate interplay between the two, and hopefully it works, and it's, you know, your standard two-actor concurrency problem. So we want our logic to be in one place, but we also want to be able to specify code that actually executes on the client. We don't want a round trip between the client and the server all the time. So can we address all these issues with language technology? We're DSL people, so we're going to try to do it that way. So initially, Andy locked himself in a room for a weekend and explored some of these ideas with Blank Canvas, which is a library for dealing with the HTML canvas element that he wrote for a FP class he was teaching. And if you want more information on Blank Canvas, it's interactive. You can do stuff. This is a little demo that hooks Blank Canvas up to an FRP library that our postdoc threw together. So, and a lot of what I'll be talking about today extracts ideas that came out of this work on Blank Canvas. So just as an overview, I'll talk really briefly about Scotty, which is a shallow DSL for specifying RESTful web services. And I'll review what shallow versus deep means here in a second. And then Kansas Comment, we'll spend some time talking about that. This is what allows the server to control the client. And then Sunroof is a deep DSL that compiles to JavaScript. This is how we say, take this piece of logic and execute it on the client. So I was going to review this in more detail, but thankfully Fritz this morning basically handled this. So shallow DSLs you can think of as kind of combinator libraries. They compute in the types of the host language. So this is a tiny little fragment for like a binary logic DSL. And then if you go to the deep version, instead of computing with the types of the host language, you build this data structure that represents your computation. And so now your combinators just use the constructors and you build up the structure. And you can see PathAdder is the exact same code that we had in the shallow version, but now I can see the actual structure of the computation, I can optimize it, I can do whatever. So this is the difference between shallow and deep that I'll keep saying. Is everybody cool with that? Okay. So Scotty is a shallow DSL. This design is largely stolen from Sinatra, which is a library in the Ruby world. We call it Scotty because it's Sinatra put on Warp. Warp is ESOD's web server. Why didn't we just use ESOD or Snap? A lot of times these web services are specified just by their URLs, and it'd be nice to just have like a little DSL where you could transliterate that specification, which is what we wanted. So a page is a triple of a verb, a URL pattern, and the content that you return when you match that pattern. It doesn't have any notion of templating languages or persistence layers. We use invars a lot. And Warp supports this very simple API where an application is just a function between request and response. And middleware is a way to wrap applications inside of each other. So Scotty just generates this application out of its DSL. So tiny little hello world example of Scotty up there. What's happening? You have your main function, which runs the web server, listens on port 3000. You have one URL route, which matches the HTTP GET. There's put, post, all the different verbs. And then that word part is the URL pattern. So the colon word is what we call a capture. So you can think of it as a named wildcard. So any URL that has a slash followed by something will match this, and the parameter word will match whatever that something is. And so you can get the parameter out of the environment, and then you can print a string. There's some types. I won't go super into detail because it's not that important, but you have two levels of monad going on here. One, which is the top level, which is essentially a writer, which keeps track of all your routes. And then the inner monad actually handles, reading out of the environment and all that kind of stuff. So if you're interested in that, it's on package. Go look at it. This is the classic Haskell strong type systems bias something. So in Sinatra, in the Ruby world, if you have these two routes, they not only overlap because they're both just a slash followed by some capture. So you would have to do some ad hoc runtime type checking. You'd have to write in there a line that says check if all these are digits or something like that. Or a lot of times you use regular expressions for this. In Haskell, we know that x needs to be an integer because it's being added to an integer. We know down here the word needs to be a string. So we can, this is a very simple type class thing. We can just make param only try to parse strings there, or only try to parse integers. And if it fails, it'll go on to the next route. So simple little thing where Haskell buys us a little bit something over the original implementation of this pattern. So anyway, that's enough about Scotty. I told you about it because we use it for the rest of this. So comment is a web design pattern essentially where the server can push to the client, push data. We implement this where the server can push arbitrary code, JavaScript code, to control the client. And it also maintains a session, so you can have multiple clients that are all hooked up to the same server, and code for one will get sent to the other and all that kind of stuff. So this is all just handled for you by this library. And just to show you kind of the request response cycle, the client sends something that says, hi, I'm here. This is the initial request. And so the server responds a worker that corresponds to that client and sends back a unique ID number to the client. So that way the client on every subsequent request can send that ID and the server knows who it is. And so what the client does is if there's a new event generated, somebody clicks on something, the mouse moves, whatever events we happen to be watching, it'll post that event to the server, which puts it into a queue. And the worker over here has been sleeping and waiting for something to show up in that queue. And so when something shows up, it'll do whatever the work is and generate a response, which is sent back to the server, put it in a queue. And then the next time the client checks for responses, which it, in our implementation does every 3 seconds because that's a phone number, it will pull back that JavaScript and run it. So the client is sitting here spinning, just checking every 3 seconds, and whatever events are generated, it's also sending those. The worker is sitting here spinning, waiting for events to show up, and the server's just in between to handle the HTTP stuff. So that's exactly what Kansas Common does. So as an example, a tiny little fib application, you can interact with it. We're using jQuery UI stuff here. And so every time I change this number, it's going to the server, server's computing, well, the worker thread on the server is computing Fibonacci and then sending it back. You can see as we get bigger, it takes a little bit longer. And this is the HTML for that page. I'm just showing you that we're not doing anything crazy. We've got 3 buttons and this span that turns into that slider, which is just a jQuery UI object. And on a JavaScript library, which just has some bootstrapping functions. This little ... of JavaScript is just that. I'm not sure if you've ever looked at jQuery before. The $sign is the jQuery object. So it says use jQuery to get the document, and then when the document's ready, run this callback function. And all we do is we have this function called connect, which connects to the server and handles everything for you. And then these last two just tell jQuery UI to turn all buttons into buttons and turn the slider into a slider. So this is really easy to write. On the server, this is the server portion. Most of this stuff in the middle here is just to do with which static files to serve. This is another little tiny, I guess you would say, shallow DSL for specifying like a security policy of which files we actually want to serve. The important part is this KC connect down here, which just takes some options and spawns a web app. And that's the Scotty code that you would write. That lift.io kcomment plugin up there, that's just to get the location of the JavaScript file. It's packaged up in the call, so you don't have to mess with that. And here's the actual web application logic. So at the very top, web app is what gets called first. So whenever a client connects, it'll run this, and what it does is it tells the client to listen for slide and click events anywhere in the body. And then it forks this control loop, which is just going to loop forever. It's going to wait for an event to come into the event queue and sleep until that happens. And then it's going to look, pattern match on the event, and do something with the model. And so the view, all this is this is the part that generates the actual response. And we're just concatenating strings here, JavaScript code, that say change whatever, change the slider value or change the response on the Fibonacci output. And obviously, we'll see the definition of before. So this is really nice. The astute observer might go, well, where did the slide and the click events come from? Because that seems magical. And we have another little mini combinator language for doing that. We could probably define most of these and just hand them to the user, but you can also match any custom event if you wanted to. So you can say, I have some data structure that's going to represent my event, and slide corresponds to the string slide, which is the jQuery name for the event. These are little code fragments that will come in the event, and those get mapped to fields, name fields. So anyway, that stuff doesn't come out of thin air. You can define your own, and it's also handy. So I hope everyone has kind of the idea what Kansas Comma does. The issue is if we wanted to create this app, which is stupid and just follows the mouse and draws circles. It's a mouse move event, so those get generated really quickly. And if we had to go to the server every time a mouse move event gets generated, that's not going to be very performant. Just that little drawing there, I'm sure generated like 1,000 of them. And especially if you go over the internet, this is all obviously local host. If you go over the internet, you have latency and all that kind of stuff. So what we want to do is we want to take the inner loop of this, which is this little do block here, and we want to compile that down to JavaScript and send it to the client and say, when the mouse move event happens, just run this JavaScript, and then wait for the next mouse move event. Don't contact me again about this. So to compile this little fragment, we have to deal with this bind to C right here. And we weren't sure how to do that at first. The issue is if you want to compile bind, you can compile the left-hand side of bind, and then you get to the right-hand side and you have this function. And what do you do with that? We need to invent an A out of thin air, which is hard to do for any A. So we were going to just kind of give up on having an actual monad and create this thing that was kind of like bind that had this extra class constraint that said we can create A's out of thin air. And we were just going to have to use explicit syntax to use this. And then we can just add return and bind as constructors to our language. And then the monad instance is really easy because these types match up perfectly. The problem would be you still don't know that this A right here is something that we can reify. Sorry, I turned reify into sunroof because that's what it's actually called here. We don't know that that A is reifiable still, but we actually do. And the reason is because we can turn any bind here. Actually, this might be easier just to draw. You have your computation. You know that at the leaf you have nothing but calls. So when you pattern match in this bind, you can look at this. If it's also a bind, you can rewrite this. And all you're doing is eventually you're going to end up with call, call, call. Using the associativity rule to do a leftmost deep depth first traversal. And you end up with this nice linear list of just primitive operations. So every time we compile a bind, if the left side is also a bind, we can just rewrite it, moving the binds over. Return we can get rid of. These are just the associativity rule for bind and the left unit rule for return. And then we have our primitive things. And the key thing is, since this is GDT, when this gets pattern matched, we bring that sunroof A context into scope. And so now we know that M is something that we can make an arbitrary value for. So we did this and we were excited. And then we submitted this paper and Heinrich Appelmus pointed out that, oh hey, somebody's already done this, namely himself, in the operational package, which is based on ideas by Lin, I believe, in ICFP 2006. He had a paper on Unimo that does this. And the insight there is that a monadic operation can be represented as a series of primitives. And so you can rewrite your tree of binds into just a list of primitives there. Also, I don't understand this well enough to actually draw the parallel, but I understand that free monads and codensity essentially are doing the same type of idea. So this has been discovered and rediscovered. So that was, from a language's point of view, that was the interesting part about how sunroof is implemented. And going back to our original example, where we did the fib, this is the sunroof version. We have to be a little bit crazier here. So what we're doing is that sync doc is compiling this whole fragment all the way down. Let's just go down to here. It's compiling that whole fragment and sending it over to the client. And so what we do is create an object to represent the model. And that just has a field that's the number that we're looking at. And then it's going to have three functions on it. One is the Fibonacci function, and then the other two are the control and view loops. These pretty much parallel the control and view loops that we had before. The syntax is obviously quite a bit different. So we're still waiting for a slider or click event, and when we get that, then we look up whatever numbers in the model, and then instead of that case where we get do nice pattern matching, we have to have a switch combinator, which gives it one type of event. And then it updates the model field on that object with a new value, and these are min and max values here. And then it calls the view, which does essentially what it did before. It changes the slider and changes the fib output. So is this a win as far as writing this versus JavaScript? That's still to be determined, I think. This is fairly early stages of this. But like I said, we have the advantage that all our logic is specified in one place on the server. We don't have to have basically two application code bases going on. So to summarize, these are our original motivating points. Browser-based frameworks are stable and they're everywhere, and it makes it easy to write a GUI. And more importantly for us, other people maintain those and make them work. So Kansas Common allowed us to put all our code in one place, which we like because it's easier to maintain that way, it's easier to write. And Sunroof allows us to send code over to the client. Whether it's better than writing straight up JavaScript, it's not entirely sure, but maybe at some point it will be. And it was at least interesting to implement because of this redefining one issue. So, thank you very much.
Questions? So, there's a question, please.
Have you tried to do this trick with other structures, like functors, arrows, applicative?
I haven't personally. I'm not sure. I don't remember the Unity paper that well to know if he did it with other things. So I think he was specifically looking at monads. So I mean, applicative functors, you don't have the same issue, right? Because you don't have this function that you have to get past. Arrows might be a different case.
So with the applicative functions, you do have the arrow that you want to get past, because on one hand side of the cross, you have sort of all these functions that you would like. So you actually have the problem, but many times more. If your applicative is like a collection of something.
Yeah. Okay. Yeah, maybe I shouldn't comment about it without actually thinking hard about it first. So.
Other questions?
So is it the only associativity that gets the job done here, or it's the other properties of monads that help you out?
Well, in this case, we're only using the associativity. So, like explicit, we're only using associativity. Because, like I said, what we want to end up with is a stream of primitive operations. And so, that's what allows us to get to that. Not sure if that's...
But I think the fact that the return is the left identity also helps you out.
Oh yeah, sorry. I hope I said that. Yeah. Return is the left unit, so that's the other rule that we're using here.
So there might be some general pattern here. So this the question about the other structures. Maybe one could characterize what properties do we need to get to the first constraint operation.
Yeah.
So for example, I tried this with functors, and they're actually fusion that allows you to get to the first constraint. So you could have constraint functors in this way, but it remains to the theme what exactly you need to perform this trick for other structures.
We should talk about this afterwards. I'm interested.
Other questions? Great, thank you very much.